Hi to all. In this video, we're going to see about choice of number of poles. Okay, in order to decide the number of poles. Okay, before going that number of poles, if you go for more number of poles, spark over may occur in that particular machine. When you go for less value of number of poles, what will happen? Uh, the magnetic flux will not be a uniform one. So the choice of number of poles is the very crucial one, and how we choose the choice of number of poles is a very important point when you go for machine design. Okay, in this there are some factors will be affected by the choice of number of poles. In order to decide the what number of poles more or less it is used to be used, let the different factors affecting the choice of number of poles be discussed based on the use of more number of poles. Okay, one is frequency. Okay, so the frequency value will change. Okay, if you go for number of poles more or less. Okay, at the same time, weight of the iron used by for the yoke also will change, and weight of the iron used for armature core that also will change. Weight of the overhang copper that is also changed. The armature reaction, the overall diameter, length of commutator, flashover, and labor charge. Okay, so these are the things will affect when we choose the number of poles. Okay, so first one is the frequency. Okay, as the number of poles increases, the frequency of the induced EMF F is equal to Pn by 120. So F and P frequency and number of poles are in directly proportional. When the it increases the core loss, and in the armature increases, and therefore efficiency of the machine will decreases or reduced. Okay, so if we go for high value of number of poles, what will happen? The frequency of the machine will be increased. When the frequency of the machine will be increased, at the same time the machine efficiency will be reduced. Okay, second one, weight of the iron used for the yoke. Okay, so here the weight of the iron of the yoke will be reduced. If we go for number of poles will be more. Let's see how. Okay, since the flux carried by the yoke is approximately pi by 2, and the total flux pi t is equal to p pi is the constant for a given machine flux density in the yoke. Okay, so by is equal to pi by 2 cross sectional area of the yoke ay. Okay, so pi r by 2p ay. Okay, so this is actually equal to 1 by p into number of poles into ay cross sectional of the there. It is clear that ay is the cross sectional area of the yoke is proportional to 1 by p. 1 by p in the sense number of poles inversely proportional to cross sectional area of the yoke. So if the number of poles are increased, what will happen? The cross sectional area of the yoke will be reduced. As by by is almost constant for a given iron, thus the number of poles increases ay, and hence the weight of the iron used for the yoke is reduced. Okay, so third one, weight of iron used for the armature core. From the core loss point of view, since the flux carried by the armature core is pi by 2, eddy current losses in the armature core is directly proportional to b square f square. So if you do the derivations or do the calculations, you will get the weight of the iron used for the armature core reduces as the number of poles increases. So weight of the iron used for the armature core reduces. Weight of the iron used for the yoke will be reduced. Okay, these are the advantage when you go for number of poles will be high. At the same time, when you go for high value of number of poles, what will happen? That frequency of the machine will be increased. When the frequency of the machine will be increased at the time, that output efficiency will be reduced. Okay, the fourth one, weight of overhang copper. For a given active length of the coil, overhang alpha pole pitch goes on reducing as the number of poles increases. As the overhang length reduces, the weight of the inactive copper used as the overhang also reduces. Okay, so here A, AF, AF, this one, AF is the active length of the coil, and ABC or ADC overhang. A, B, C and A, D, E. Both are inactive part of the coil. This A, F and this one will be the active part, and these two are inactive part. Pole pitch increases of 4-pole machines. Okay, so overhang copper will be also reduces when you go for number of poles are more. Okay, so armature reactions, since the flux produced by the armature and armature ampere currents, since the flux produced by the armature pi a is equal to ATA by pole by reluctance, and the armature ampere turns ATA by pole, so that is equal to IA Z by 2 AP is proportional to 1 by P. So pi a reduces and as the number of poles increases. This is turn reduces the effect of armature reactions. Okay, so if you go for number of poles will be more, then the armature reaction also will be reduced. The copper used for the machine will be reduced. The iron used for the yoke as well as iron used for the core will be reduced. Okay, the overall diameter. Okay, when the number of poles is less, ATA by pole and hence flux produced by the armature is more. This reduces the useful flux in the air gap. In order to maintain the constant value of air gap flux, the flux produced by the field or the field ampere turns must be increased. This calls for more field coils, turns and size of the coil defined by the depth of the coil df and height of the coil hf. Hf is nothing but height of the coil and df is the depth of the coil increases. In order to that the temperature rises in the coil is not more. Depth of the field coil is generally restricted. Therefore, height of the field coil increases as the size of the field coil or the number of turns of the coil increases. As the pole height is proportional to the field coil height, height of the pole and hence the overall diameter of the machine increases with the increase in height of the field coil. Okay, obviously as the number of poles increases, the height of the pole and hence the overall diameter of the machine decreases. If you go for number of poles high, then the size of the machine will be decreased. Okay, see here, diameter of the case of two-pole machine, the diameter will be very high. At the same time, when you go for the same efficiency, the same output of the machine of four-pole will be small. Okay, so length of commutator, since such brushes arms collects the current from every two parallel paths current per brush. Okay, so reduce the number of poles increases. So brush, spindle, arm or older commutator segments. Okay, flash over is a major one. When you go for here, number of poles will be high. Okay, if you number of poles high, then that poles are very near. Okay, each poles, the north pole and south poles are very near. So the spark power may occur because the high voltage, high current will be lost in that motors or generators. Sometime the nearby will be affected. Okay, as the number of poles increases, the voltage between the segments EB is equal to voltage between positive and negative brushes divided by number of segments per pole increases. Because of the increased the value of EB and carbon dust collected in the space between the mica is undercut. Chances of arcing is a major one. Okay, when you go for high value of number of poles between commutator segments increases, the arc between the segments in turns may bridge the positive and negative brushes, leading to a dead short circuit of the machines. Okay, so labor charge, when you go for number of poles are high, then the labor charge for the making or fixing that number of poles in a particular machines will be high. As the number of poles increases, as the labor charge increases, as more the number of poles are to be assembled, more field coils are to be wound placed on the pole insulates interconnects. Okay, so it is clear that when the number of poles are more, higher value of iron used, lower value of iron used and lower value of copper used. Okay, since the advantage of overcomes advantage, more number of poles is preferable. Okay,